We're gonna kind of continue on with chapter 4. So again, for chapter 4, these are all covering topics that we've already seen before in a trigonometry or geometry class or elsewhere. So I'm just going to kind of do some review examples. We might settle in and rediscuss something if it feels like there's a gap or whatever, but for the most part, this is all stuff we've done before. So we're not going to the plan is not to be super thorough unless you decide that we need to. So first question says, by drawing an appropriate triangle, calculate, for example, sine of 120. So to do this, I'm going to start by drawing my xy axis. If I want to draw a 120 degree angle, I know that the initial side starts on the positive x-axis, and we rotate from that initial side counterclockwise, and then 120 degrees. So it looks something like this, right? Where that section is 90 and that section would be 30. Everybody feel good there? Now the triangle that we're going to make is always going to go down to always to the x-axis. Good morning. Paulie, looks like you're going home early today. Everybody's okay there? That's a right triangle. You're welcome. And notice that this angle has to be 60 degrees. How did I know that was going to be 60 degrees? Because the 30 degree angle next to it, right? Has to be complementary. So that angle is 30 degrees. So what I'm looking at here is a 30, 60, 90 triangle, correct? Okay. So I know that the side opposite the 30 degree angle is the short side. The side opposite the 60 is root 3 times a, and the hypotenuse is 2a. Everybody's okay there? I do need to make one little adjustment because I'm in quadrant 2. I know that the x coordinate is negative and the y coordinate is positive, right? So this label that I've given to A that's going left and right, that's like a x value, I'm going to make negative. The hypotenuse will always be positive, but I can label those x and y's positive or negative depending on the quadrant. So far, so good? Now, this angle here is what we call our reference angle. So sine of 120, and I'll call that reference angle theta, is going to be equivalent to sine of theta. So that's going to be opposite over hypotenuse. So my answer should be root 3 over 2. Joey? It's always the one that shares the arm with the x-axis. Does that feel okay? You guys kind of remember doing this in trigonometry? Do we need to do more examples of this, or do you guys feel okay? It's good? Okay. Doesn't really change any, right? It says show that for any angle between 0 and 90 degrees, sine of 90 or sine of theta equals sine of 180 minus theta. That's exactly what we just did in the previous example. Or what we observed in the previous example, that sine of 60 was equal to sine of 120, right? Why is that going to be the case? Well, let's just say, where does it fail? Right? Could I say the same thing if I did, like sine of theta equals 360 minus theta? Does it work for things in the lower half of the xy axis? Like if my reference triangle was down here in this part, will that be true? No. Why not? I know for sine of angles between 180 and 360, the sine is negative. But that reference triangle angle would always be positive. So like that's the issue. So this works because sine is positive for all values between 0 and 180. Let's see what our textbook did when they decided they were going to show that. Oh, that's so stupid. Why would I want to take this thing? All right, let's see what they did. Okay, that's fine. So their explanation was like, if I draw like angle theta here, this is some point like x comma y, right? Where this is like my distance x, that's my distance y, and I'm just going to call this distance for the hypotenuse z. If I do sine of 180 minus, that's still the point xy, right? Because this angle and this angle still have to be the same. So I'd have like sine theta is y over z, and sine of 180 minus theta is still going to be y over z. So they did it geometrically as their explanation. Does that feel okay? So they just kind of drew a picture and made some observation. Part B says find two different angles theta with sine theta equals 0.65. Well, one of them should be quite easy, right? I can just do sine inverse of 0.65 to get that value. What mode should my calculator be in to do this? Yeah, always degrees in this class. No radians at all. So just do sine inverse 0.65. And that's 40.54. And then I could do something as simple as by part A, I know that it's complement supplement would also equal the same thing, right? 139.46 could be my second angle. Is everybody okay there? What else could have you done, though? Remember your trigonometry. I wanted another angle that also has sine of 0.65. What else could I have done? Just found an angle coterminal to 40.54, right? That's still going to be this, give you the same value, right? Everyone's okay with that? That angles that are coterminal are basically like fractions like 2 over 2 and 4 over 4 that are it's the same number. Angles that are coterminal are kind of like the same angle as far as sine, cosine, and tangent and stuff is concerned. Part C says, show a triangle containing an obtuse interior angle theta and two enclosing sides with lengths A and B. The area given by the formula 1/2 A. The area is given by the formula 1/2 AB sine theta. Nah, to be honest with you. I mean, it's like I wouldn't ask you to do this, but here's the idea. Like, okay, here's our triangle. There's my theta, right? So I'll call this side A and this side B. So the idea is that this is like I thought I was going to do that. Stupid thing. That this angle is like 180 minus theta. And this side here is like the height of my triangle, right? So if my triangle is 1/2 base times height, and that height is going to be the same thing as, I can say sine of 180 minus theta equals opposite over hypotenuse. So that'd just be like height is B times sine of 180 minus theta. And I know that sine of 180 minus theta and theta are the same if theta is between 0 and 3 or 0 and 180, which is just what we did before. So we're done. Okay. So part A says, or the next example says, find the value of the missing side length x in the triangle shown in figure 4.27, correct to 2 decimal places. So if I look at this triangle, what do you notice is the complication here if I'm looking to find this side x? So, I mean, is that a problem or no? Is there a complication here? Well, what is this angle here? How much is that? Yep. So it's 90, right? So is there any kind of complication here? No, what should we just do? It's SOHCAHTOA, right? So let's pick an angle to use. Does it matter which angle we pick? Not really. For the sake of argument, let's do the 25 degrees. Relative to the 25 degrees, the side we know, the 14, is opposite, adjacent, or hypotenuse. Great. And the x, the side we want to know, is opposite. So the trig function we're going to use is sine is opposite and adjacent? Because it looks like opposite and hypotenuse is what I need. Tangent. So tangent of 25 is opposite over adjacent. So x is going to be 14 times tan 25. Everybody okay there? No big deal, right? If it's a 90-degree triangle, nothing has really changed. What about something like, or if it's a right triangle, excuse me. What if we have something like this, though? Well, do we know that it's a right triangle? No. Can I use SOHCAHTOA if it's not a right triangle? No. What are the tools I need for non-right triangles? We have two tools that we might use. Law of sines. And then law of cosines. For law of sines, we'll do that when we have two angles. So if we have like an angle side angle situation or an angle angle side situation, or if we have that dreaded side side angle situation. Law of cosines we use if we have a side 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 or a side angle side situation. So which situation do we have here? So this is what we're given, right? That is not side angle side because the given angle isn't in between the two sides. This is side side angle, right? So if it was side angle side, I'd have to be given this angle where the two sides form the angle. So this is an SSA case. Now, if you remember back your trigonometry, sometimes these SSA cases can get rather nasty. That won't happen in this class. So that's nice. So if I want to set this up then, I'm going to say that this is like angle A, and the side opposite is going to be side A. I'll call that angle B, and the side opposite then is side B. So we'll say sine of 60 degrees over 9 equals sine of theta over 10. So we'll cross multiply, so that's sine, or 9 times sine theta equals 10 times sine 60. We'll divide both sides by 9 and then do the sine inverse. I'm going to do that all in one step. And now it's calculator time. We get about 74.2 degrees. Does this all look familiar? You guys remember doing law of sines last year in trigonometry? Okay. All right, let's take a look at these ones. So if I look at part A for this, which we're looking for that third side x, which situation are we in? Are we in a law of sine situation or law of cosine situation? Very good. So this is the side angle side situation because I see that the two given sides make up the given angle. So if I plug this into law of cosines, I'm going to have x squared equals 5 squared plus 4 squared minus 2 times 5 times 4 times cosine 30 degrees. So that just is all going to go into my calculator. The most common mistake students make is they forget to solve for x, that you're not solving, they solve for x squared. Oh, Mr. Kulik. You just got to be careful. Yes. You can label them however you want. So they're just names. So like whatever label you want to give to things. The thing you have to remember is that the side opposite the angle has to have the same letter name as your angle. So your angles are your capitals. So like if I call this guy angle A, that side opposite has to be side A. If this is side B, the side opposite has to be side B. If that's angle C, then the side opposite has to be little c. That's the only thing you have to worry about for consistency. But after that, you relabel things if you need to, whatever makes it easy. It's just names. The convention of how we're doing the naming is important, but the labels you're putting on there, not important as long as you're following the convention. So we did all that, and we get then that x is 5.69. Oh, no, it's not. I forgot the 4. I was going to say, I found that hard to believe that that side was going to be bigger than the 5. Okay, try that one more time. 2.52, that makes more sense. So as a little reminder here, and this is a good check, is that I remember from geometry that the side lengths and angles in my triangle are proportional. So that means that like the smallest angle should be opposite the smallest side. Like the biggest angle should be opposite the biggest side, and the middle angle should be opposite the middle side. So 30 was a pretty small angle. I found it hard to believe that that was the biggest. If this side was 5.2, that would make 30 the biggest angle in my triangle. Can 30 be the biggest angle in a triangle? Nope. That's why I was like, how I knew just by looking at my answer that I had done something wrong. I forgot a 4. Oops. Next up, we're looking at part B. Which situation or which formula do I need? Okay, so that's a side angle side situation, so I'll be using law of cosines just like before. So again, I'm going to write it down like this. I'm just going to type the square root, though, into my calculator. And I'm not going to bother to write the square root of 17 squared. I'm just going to write 17. Is that okay with everybody? Like, I'm not making a typo. I'm doing that part, at least intentionally. This time I'm going to remember to type all the numbers, though. So I get 979. How you guys feel there, okay? All right. So on this one, we're going to be asked to find the angle. Which law do I want to use? Law of sines or cosines? Good, law of cosines, because it's a side situation. So to set up the law of cosines, the thing that matters is that the side opposite the angle that I'm solving for, that's the piece that needs to be by itself. And now we just need to solve for the theta here for cosine. So to do that, I'm going to start by subtracting over the parts that are being added. Right? Then I'm going to divide over the part that's being multiplied to my variable. And then I need to cancel out the cosine that's wrapped around it. And now it's just calculator time. Now, for a problem like this, I strongly recommend using the fraction command on your calculator, because it's kind of a nightmare to get this fraction in there in the right order. Otherwise, very easy to make a typo. So we get 62.9, or I should say, well, like 63.0. Everybody okay there? Do we need to do the second example? Same idea as the first, right? No real difference. The key part, though, that we have to make sure that we don't screw up is that the angle that you're solving for, that's the angle in the cosine in the formula, and the side opposite that angle is the lone side in the formula, right? If you goof that up, then you're not going to get the right answer. You got to get the stuff in the right spots. Next example. For the triangle shown below, find the missing side length, find the missing angle, and then calculate the area of the triangle. All right. So if I look at the missing side, what given information do I have? It looks like I have a side angle side situation, right? So I should be using law of cosines. So into my calculator she goes. Yes, sir. Yeah, can you leave me like a piece of collateral or an IDs or? Sure.
I can't even leave this.
Can't leave school without it.
Thank you so much.
Yeah, no problem. Good luck on your test.
Thank you.
Sure thing.
We got one that's got a really high charge. Just in case.
Yeah. Yeah, I haven't been at school in a couple of days, but take a look at what you got. Is that better? Okay.
Yeah, this one's full. Thank
Okay.
you.
Will you do me a favor and plug this one in for me?
Yeah.
There's a set of chargers right there on in the power strip there. Just so the next person that comes by looking to borrow one isn't out of luck.
Yeah, thank you.
Yeah, no problem. Have a good one.
You too.
So there's that. No problem there. Part B now. So if I look at part B, how am I going to do that? So I could use either now the law of sines or the law of cosines, right? Because I have that additional piece of information that now makes this a situation where I could treat this as an SSA case or an SSS case. It doesn't really matter. You guys agree with that? So what I would do is probably just use the law of sines because it's a little bit easier to get the angle by itself than the law of cosines. So I'm going to say I have sine of theta over 30. And then I need the angle that I'm given, so that's sine 27 over the side opposite to us, which is now that 16.2. Does everybody feel okay there? Do we need to show the algebra to how I'm going to get theta by itself, or do you guys good with all that? Okay. I have one thumb up, so I'm just going to go with it. So that's going to be 30 times sine 27 divided by 16.2. I, like a dummy, didn't leave myself enough space to write my sine inverse. So when I plug that into my calculator, I get 57.2. And then part C wants the area So I notice that I have a side angle side situation. That's what I need for my area. So I don't have any additional work to do there. I could have done these problems the only one that I had to do A before I could do B. So the area is like 1/2. The formula is AB sine C, but it's basically if you have a side angle side situation, like we do, it's just 1/2 leg times sine of the included angle. So all that area formula requires is like a side angle side situation, and it's just like 1/2 leg times sine of the angle is the formula. Does that feel good? Which is massively simpler than trying to figure out like a height for this thing, right? Like, what a nightmare. All right. You guys remember these bearing problems from trigonometry? Oh no. It says an aeroplane. We're still in Britain apparently, flying our aeroplanes instead of airplanes. Flies 280 kilometers on a bearing of 9 degrees from Calgary, Alberta in Canada, as opposed to Calgary, Alberta in Mozambique or something to the provincial capital, Edmonton. From Edmonton, the plane flies 1,320 kilometers on a bearing of 72 degrees to Churchill, Manitoba, located on the shores of Hudson Bay. How far is it from Churchill to Calgary? When you guys did these types of problems in trigonometry, AP Trig kids more than the regular, because I taught the regular kids this last year, so I know how we taught it last year. How did you guys? How was this approached? Yeah, I'm asking the AP kid. I know what we did, right? Because I did it for you, right? So I know the AP kids. I want to hear how you guys approached one of these. Did you do this as vector problem, or did you do it as a triangle problem?
Everyone had like a million steps of I don't remember them.
Oh, sorry, pre-calc. Yeah. Okay, so you guys don't remember doing this at all? I hate the way the book does this. I hate using the law of sines and cosines on it. I think it makes it impossibly hard to deal with like getting a decent picture and like making sure you can figure out the angle values and stuff. Like, I think it just makes it harder than it needs to be. I'm going to approach this all from a vector standpoint because AP pre-calcers did vectors. Regular trig kids did vectors. We did this all last year. So I'm going to do it this way. Everybody's okay? All right. So what I'm going to do is I'm going to draw a picture for, when I read this, I hear this journey has 2 legs, right? I go from Calgary to Edmonton, and then I go from Edmonton to Manitoba or to Churchill, right? So what I see is that I'm going to have 2 vectors, one for each leg. So I'm going to draw a picture for the first vector. So that's a 9-degree bearing. So starting from the north, remember bearings are weird, and instead of starting from a standard position angle, they start from the north line. I think it's a leftover from like nautical navigation in like the Middle Ages, where if you had a compass, the only direction you knew for sure was north. So I'm going to draw that. And the length of that vector is 280 kilometers. What I want to do now is I want to resolve this vector into like a standard position angle. So what is that angle theta going to be here? Should be quite easy, 81 degrees. So if I rewrite my vector, I'm going to call this one vector v. If I write it in component form, that's going to be the magnitude times cosine of my standard position angle, comma, magnitude times sine of my standard position angle. And I'm going to draw a picture for my other vector. So this is 72 degree bearing. I'll call this vector u. And this is a long one, 1320. So again, the first thing I need is that standard position angle. So if the bearing was 72, what's the standard position angle going to be? Yes, 18 degrees. Yes. Yeah, I guess. Yes. Yeah. Always cosine for the x coordinate, always sine for the y coordinate. Is everybody so far so good? So now if we add these two vectors, the result, I'll call that vector r, is going to be end up like the path from the start to the finish, right? So the idea is we're at like the start, we do vector v, and then we do vector u, and then we'd have like some vector r. Everybody's okay with that idea? So the length of vector r is going to be the length of the journey. And the standard position angle for vector r we can translate into a bearing if we needed to, but this question is even asking for that much. Everybody's okay? So part A is just asking us for the magnitude of r, because it wants to know how far is it from Churchill to Calgary. So we went Calgary, we went to Edmonton, and we're ending in Churchill. So I'll compute r to start. So that's my x component. And that's my y component. So 1299.2 and then 684.5. So then to find the length of that vector, I just basically do the Pythagorean theorem on it. So I get about 1468.5. Yes. That is not an absolute value symbol. Those vertical bars, when they're around a vector, mean magnitude. So they're the length designator. And to find the length is just doing the Pythagorean theorem. So it's like the square root of a squared plus b squared. So the vertical bars, when they're around a number, mean absolute value. When they're around a vector, it means the magnitude. If they're around a matrix, it would mean determinant. So they're just like, it's a symbol that gets really abused. But that's the idea there. And I would rather, me personally, I would do all of my navigation stuff using vectors as opposed to like trying to draw a triangle and do the law of cosines on it. It's equivalent process, but like to me, this is so much easier because it's the same like every single time. There's no geometry involved, and like if I draw a good picture or a bad picture doesn't really matter. Where if I doing the by law of cosines, if I draw kind of a crummy picture, it really hurts me. Part B then says if the airplane flies at an average speed of 720 kilometers per hour, how long does a direct flight? So I'm just going to take that answer and divide it by 720. So I get about 2.04 hours. How'd you guys feel on this law of sines and cosine stuff? I strongly encourage you to do this homework assignment rather than just like copy down the answers from the back of the book. Is like there's a fair amount of detail involved here that like we've done, and I know you guys know how to do, but like probably would be a good idea to do a little bit of practice to make sure you're all the way back up to speed. 4.4 is going to be all about calculating surface areas and volumes of these like three-dimensional solids. So I just kind of info dump some common figures here and how to find their surface areas and their volumes. So these are formulas that you would be given. They're not things that you need to memorize, but you probably know some of them already. So let's just go ahead and dive right in. So it says an ice cream cone has the shape of a right circular cone with a radius of 3 centimeters and a height of 8 centimeters. Calculate the volume of the cone. If I go to my formula sheet here, it says the volume of a cone is 1/3 pi r squared h. Do I have what? On top of the file cabinet, it's a whole big stack of Rooney of them. And while there's nothing much really to do here, I'm just like plugging them in, right? And then it's calculator time. I'm not going to bother to type it through on the calculator if you guys are cool with that. And then it asks for the surface area. So I go back to my list. The surface area for my cone is pi r squared plus pi rs. And if I look at my picture, s is like the slant height of the cone. So it's like that hypotenuse. So I need to find s. So s is going to be the square root of 3 squared plus 8 squared. And that's 73 is 9 plus 64. Oh, I'm so dumb. I made a mistake here on part B. And the mistake is not with any kind of mathematics, it's a reading mistake. With part B, there's a mistake that I made. It's a reading mistake. Can anybody see it? What is this cone used for? Ice cream cone. So, does it have a circle as a surface? It's open, right? So that part shouldn't be there, right? That pi r squared would be if it's like a solid all the way through. You guys see that? So that shouldn't be there. So the S is like, this is like our, it's like the slant height. So the if I draw my cone or whatever, if you go back up and look at the picture, it has where the S is labeled on the picture. Yep. Yep. All right. Let's do another example. A spherical rubber ball has a radius of 10 centimeters. Calculate the surface area and volume and interpret your answer. I don't know what interpret your answer would be. So the volume for a sphere, if I go back and look, is 4/3 pi r cubed. Yes? Oh, that's a good question. It's a shortened period today. I think it's the same time as a mass schedule. I think sure email said to arrive for if you had first hour study at 8:45, probably for passing time. It's probably 8:50. I think or
Oh, no, it is 45.
okay. Well, let's just finish this problem. You guys can go. Deal, Leo? Okay, so that's the volume. That's like how much space the ball would hold. The surface area is 4 pi r squared. And that would be like how much material you need to construct the ball. Right? Like that's the size of the sheet that you'd need to make your ball. Assuming that you could fashion a sphere together without having to do any cuts. Okay, so this is the last section in chapter 4. We'll finish this, talking about this next time. I would like to do the chapter 4 quiz next class also, and then take the last 20 minutes or something after the quiz to finish. the 4-4. Does that sound agreeable to you guys? I'll put up a quiz description later today. I think it's just 4-1 and 4-2, but I'll make sure I'm clear on that on the description. Deal? Okay. See you later, guys.